Good morning, students. Let's continue with the next property verification. Next on the series is complex conjugate properties. Under this, you'll be learning this complex conjugate property both in time domain as well as frequency domain. To begin with, let's start with time domain. The statement goes like this. If x of n is said to form an endpoint DFT pair with x of k, by the property statement, we have to verify whether x conjugate of n will form an endpoint DFT pair with x conjugate of n minus k. I told the other way of writing x conjugate of n minus k is this format, So knowing this, we should prove this below line. Let's start with the proof. To begin with, consider the standard equation for DFT, which goes like this. X of k is given by summation small n varying from 0 to n minus 1, x of n into its complex term. Since I am interested in the term n minus k, substitute k by n minus k on both the sides. Accordingly, the equation gets modified like this. In the next step, as we know that e to the power of minus j 2 pi n by n, the first term, if I've got this number n both over at this position and at this position, subscript and superscript, this term tends to 1. Accordingly, we are left out only with the term e to the power of j 2 pi nk by n and the remaining terms as it is. For the above equation, I consider its complex conjugate form. Accordingly, x conjugate of n minus k will be what? The complex conjugate of the whole of RHS. Pulling summation outside the conjugate is been applied only to the terms within the bracket. Accordingly, x conjugate of n is been written separately and complex conjugate of e to the power of plus j 2 pi nk by n is nothing but e to the power of minus j 2 pi nk by n. As I've told earlier, complex conjugate is just what? Changing the sign of the imaginary term. Hence, plus j becomes minus j, x of n becomes x complex conjugate of n. If you could observe this equation resembles the standard DFT equation. If I had x of n, this was the equation for the DFT of x of n. But in place of x of n, what I've got? X complex conjugate of n. That is why the RHS is nothing but the DFT of x complex conjugate of n. What I had in LHS? X complex conjugate of n minus k. Hence, we have proved that if x of n is said to form an endpoint DFT pair with x of k, by the very property statement, x complex conjugate of n is also said to form an endpoint DFT pair with x complex conjugate of n minus k. The same derivation is viewed in the frequency domain. The statement goes like this. Once again, if x of n is said to form an endpoint DFT pair with x of k, then instead of the shifting process in frequency domain, if I could shift it in the time domain, that is, x complex conjugate of n minus n should form an endpoint DFT pair with x complex conjugate of k. Again, in this case, what we'll do is we'll start with the standard IDFT definition, which goes like this. X of n is given by 1 by n summation k varying from 0 to n minus 1 x of k into this complex exponential term. What term am I interested with? N minus n and its complex conjugate. To begin with, let's consider x of n minus n. What I must do? Wherever n is there, replace n by n minus n. In this equation, wherever n is there, replace n by n minus n. Just similar to the previous derivation, whenever I had this term n both in the subscript and superscript, the term tends to 1. If it is so, the term I am left out with is just e to the power of minus j 2 pi nk by n. What am I interested in the next step? Take complex conjugate on both the sides. Applying complex conjugate to the both the sides results in 1 by n outside, summation term outside, complex conjugate restricted only for these two terms. Complex conjugate of x of k is x complex conjugate of k, and complex conjugate of this exponential term, complex exponential term, revert the sign or change the sign, minus j gets changed to plus j. Accordingly, what I'm left out is with this particular term, 1 by n summation k varying from 0 to n minus 1 x complex conjugate of a into e to the power of j 2 pi nk by n. And again, if you could compare this with the standard IDFT equation, this is nothing but the IDFT of this term. What is this term in the present context? X complex conjugate of k. That is why x complex conjugate of n minus n is nothing but the representation of the IDFT of x complex conjugate of k. That is why, to summarize, if x of n is said to form an n-point DFT pair with x of k, obviously x complex conjugate of n minus n is also said to form an n-point DFT pair with x complex conjugate of k. Yes, those two are the complex conjugate properties. What we have seen both in time domain as well as frequency domain. The next two derivations are based on circular convolution. Probably in the previous semester in signals and systems, all of you would have been introduced to linear convolution, that is convolving the two scales, convolving the two sequences on a linear scale. The same convolutional operator is viewed on a circular scale, referred to as circular convolution. How exactly the equation for circular convolution looks like will be seen in the following derivation. Okay, so let's start. So what exactly the statement means, you'll be able to appreciate it at the end of the derivation. Okay, so let's begin with the derivation. What I'm doing initially is considering two finite duration sequences of what length? Of length capital N. What are those two sequences? x1 of n and x2 of n. I'm considering their respective equations for DFT. Accordingly, this gives the equation for the DFT of sequence 1. The below equation gives the DFT of equation DFT for the sequence x2 of n. Now I'll be introducing a new term called as x3 of k. What is x3 of k? Represented here as the product of the DFT of sequence 1 with the DFT of sequence 2. The product of these two finite duration sequences, the product of the DFTs of these two finite duration sequences is represented by a variable x3 of k. Now, I want to translate from frequency domain to time domain. What I must do? Consider its IDFT representation. Accordingly, the IDFT of the variable x3 of k is given by, right, what the standard equation for IDFT? So in place of x of k, what am I having? x3 of k. So x3 of m is given by the standard IDFT equation. And please note that here in place of n we have got m. Any variable you choose, that shouldn't matter. Now what is being done in the next step is substitute the value of x3 of k. What is x3 of k equal to? the product of x1 of k into x2 of k, remaining all terms as it is, no change. In the next line, the first term as it is, the second summation term as it is. I'm substituting the value of x1 of k. x1 of k is given by the term within the first bracket. That is what? The expansion, the DFT expansion of sequence x1 of n. Similarly, what is x2 of k? The DFT expansion of the finite duration sequence x2 of n. Kindly note that since these are two different equations, I can't consider the same summation index tag. Here it is n, here it is L, and here it is k. Kindly note that all the three summation index variables should be different if you're using all the three in the same equation. And all this term is what? Multiplied by this complex exponential term as it is. In the next step, note that 1 by n as it is. I'm putting the respective terms within the respective summation variables. That is, x1 of n is tagged under this summation, x2 of L is tagged under this summation, and lastly, for the outer summation index k, I'm combining all the three complex exponential terms under one head, because all these three terms are carrying the index k, hence they are being tagged under this particular summation. Now a bit of some modification to get the result in the standard format. So what am I right now interested with? The last summation term. So considering the term k varying from 0 to n minus 1 e to the power of j 2 pi by n m minus n minus L times k. This whole exponential term, excluding this value of k, is designated by a variable called as a. Summation k varying from 0 to n minus 1, a to the power of k. What is a? Shown over here. Using the progressive series expansion, summation k varying from 0 to n minus 1, a power k is given by, actually what is the formula? 1 minus a to the power of n plus 1 divided by 1 minus a. In case my tag here, the upper limit is not plain n, it is n minus 1. Therefore, substitute here as n plus 1 minus 1. That plus 1 and minus 1 will get cancelled, resulting in a power n. And this formula holds good provided what? The value of this term a should never be equal to 1. What happens if the value of a is equal to 1? Get back this to its equation. If the value of a is equal to 1, what is 1 raised to any variable? It is 1. So summation k varying from 0 to n minus 1, the number 1 is represented by n. We have learned this formula sometime earlier also. If the value of a is equal to 1, the summation turns to give me a value of capital N. But if the value of a is not equal to 1, how does this term looks like? For that, recall this value a raised to the value of capital N. A raised to the value of capital N. Substitute the value of a as this particular term. As sometime back I've told you, whenever any variable comes in both subscript and superscript, that value of Twiddle factor is always equal to 1. Accordingly, what is the value of a to the power of capital N is equal to 1. Now, see, get back to this equation. If I could substitute the value of a raised to the value capital N as 1, 1 minus 1 is what? 0. This whole term tends to 0 provided what? The value of a is not equal to 1. Accordingly, we say summation k varying from 0 to n minus 1, a raised to the value of k, okay, this particular expansion will give me a value of 0 provided the value of a is not equal to 1. But if the value of a is equal to 1, the value is equal to capital N. In the next step, what we have done is translated the same equation. The only change is I'm replacing the value of a. I'm replacing the value of a by its complex exponential term. Or else these two equations are the same. Accordingly, now we'll just get back to the generalization of that complex exponential term. See, I'm not interested in this value of 0 here. As long as this term of a is not at all equal to 1, this term tends to 0, for which right now I am not interested. What am I interested with? Whenever this term tends to 1, what is the value equal to n? What is the value equal to n? So when does this term tends to 1? Provided what? I get that value of n both in the subscript and the superscript. Okay, so accordingly, consider the term within this bracket, that is what, m minus n minus l. I said this term tends to be equal to n provided what? This term is equal to minus p times n. If you ask me, madam, how did you get this equation? I try to what, recall that circular shifting operation. Yeah, circular shifting operation a mod b. What is a mod b equal to? A minus b multiplied by the value of p, where p is any integer. Accordingly, I'm taking this whole term as a and this term as b, and b is what, multiplied by this p, where p is any integer. Again, a question might arise, why is that, madam, you have taken minus value? Why can't it be plus value? Absolutely right. It can be either minus sign or it can be either plus sign. If you could revert the sign here, the value of p, whatever integer value you are going to choose, should be what, alternatively changed. So it can be either minus n or plus n. Since I want all positive terms, I've taken this as what, minus p. So if m minus n minus l is equal to minus pn, push this term towards the LHS side. This whole equation gets equated to 0. Over here, I'm interested in the summation index value L. So what is the value of L equal to? M minus n plus Pn. Treat this as the value of A and treat this as the value of B and get that circular shift property over here. So what is the value of L written as? M minus n modulo n. Please note that this n is the modulo index n, because a mod b is what? A minus b into p, the same notation what you have learned in the circular shift property. So now this value of L will be incorporated in the above equation. Which equation? Please see, we're recalling back this equation and I'm substituting this value of L as what? M minus n mod n, and this whole term is equal to what? Is equal to the value of n, provided what? The value of A is equal to 1, So we're recalling back this equation. Accordingly, what we get is, therefore, x3 of m. See all these terms, okay, I've rewritten the same equation for your convenience. See, the first three terms as it is, no change. And in the second term, the whole of the second term is replaced just by x2 of m minus n modulo n. What I'm doing? I'm substituting the value of L as m minus 2 modulo n. If you can always ask a question, ma'am, the summation index is varying from 0 to n minus 1. Why is that? You're just considering only this value of L as what? M minus n modulo n. What happened to the remaining terms? It's found that for all other remaining values of L other than this value, the summation turns out to be 0. The summation exists only for this particular value of n. For if you have got curiosity, you can take a number and check it out. Okay, that is why only this value has been retained, because all other terms tends to 0. And the third summation value, as I told, is equal to what? The value of n, provided what? The value of A is equal to 1. This term is equal to 1. By considering this term is equal to 1 only, I obtained the equation for L as what? M minus N modulo N. Accordingly, what happens is this term N and N will get cancels. The resulting equation for x3 of M is summation small n varying from 0 to n minus 1 x1 of n multiplied by x2 of M minus N modulo N. And please note that this is a standard equation for the circular convolution of two given sequences x1 of n and x2 of n. Okay. So this, see, if you could ask, if you could just what? Compare this equation with the linear convolution, in the linear convolution equation, I don't have this index modulo n. This index modulo n represents the circular convolution. As I told you, here we are trying to convolve the two sequences on a circular scale rather than a linear scale. The fundamental differences between linear convolution and circular convolution is that always linear convolution can be used to convolve any two aperiodic sequences, but whereas circular convolution is always preferred to convolve two given periodic sequences. The advantage is that for any one fundamental period, if I could convolve the two sequences, the same result gets repeated for the other intervals also. This is the second difference. The third difference is, in case of the linear convolution, the length of the convolved sequence is given by what? Length of sequence 1 plus length of sequence 2 minus 1. But whereas in circular convolution, the length of the convolved sequence is always chosen as the length of the greater length of the two given sequences. For example, if sequence length 1 is 3, if the second sequence length is 5, I always choose the higher length, that is what? 5. So the length of the convolved sequence in case of circular convolution will be 5. Out of those two sequences, whichever sequence has got the greater length, that will be maintained as the length of the convolved sequence. We'll touch upon more upon this when we are going to solve numericals. Okay. So the conclusion of the above property is, if x1 of n is said to form an endpoint DFT pair with x1 of k, similarly, if x2 of n is said to form an endpoint DFT pair with x2 of k, if I could define a new sequence of x3 of n, which is said to form an endpoint DFT pair with x3 of k, in time domain, what is x3 of n visualized as? Circular convolution of the two given sequences x1 of n and x2 of n. Note the symbol. This asterisk symbol enclosed within a circle represents circular convolution operation. But what is x3 of k equal to? The product of the two respective DFTs. So the statement goes like this: convolving the two sequences circularly, okay, in time domain is equivalent to the multiplication of the respective DFTs in the frequency domain. That is, circular convolution in time domain is equivalent to the product of the respective DFTs in the frequency domain. I'll stop this recording of this derivation over here. The next three derivation will go for another recording.